All right, we got some good stuff today. We've got the introduction to computer architecture. This is going to be a fun stream. Everything you could ever possibly want to know in one stream. Because we're going to pick between two of the most widely used books for introductory computer architecture. And I figured out how to do the low latency thing. So this is live and real time. This is the best it's going to get. All right. We've got two books here. We've got two wonderful textbooks. Classics, if you will. Both by David Patterson and John Hennessy. Teach you everything? Absolutely. Listen, you don't get to leave the stream. You don't get to leave the stream until you've learned everything. I'm laying down the law now. Can't leave. Both of abacuses? Absolutely. That's peak performance. How do I ×2 speed this live stream? Watch the VOD and ×2. Listen, I'm going to put all the VODs up on YouTube. And I can do that so quickly because I have 800 up. But what are the numbers representing? I don't know. Anything. Everything's represented by a number in a computer. Yep, there's no YouTube. There's no YouTube command yet. There's nothing yet. This is brand new. We're figuring this out together. All right. We got to pick. It's okay. This is like a web version of the book, so that's why it's 1,600 pages. It's really only like 800. Are these PDFs legally obtained? Of course. Why would these illegally obtained? Using Apple. Who's using Apple? I don't know who's using Apple here. I'm not using Apple. This is a Linux machine. I'm on Ubuntu. Because I'm literally, this is live from the lab. You guys are getting it live from the lab. There is no fresher computer architecture than from the lab. So we got to make a decision here. Now, there's not much difference between these two books. Not much, but there are some subtlety, mainly because one of them is written completely for MIPS, one of them completely for RISC-V. Why isn't this from your home? Because I don't get 800 up at my home. I don't get 800 up at my home, and I also don't have a desktop. I moved up to where my university is. MIPS is probably easier to begin with. They're the same. It's a reduced instruction set architecture. They're both fine. There's not a huge difference. I mean, if you're really learning like loads, stores, arithmetic operations, I mean, what's really the difference? I mean, this isn't like a optimization of some x86 terrible instruction set that no one... What is computer architecture? That's a great question. Yeah, that is a absolutely amazing connection. If I can get like, let's see, which one has higher Amazon review score? Doesn't matter. This is Patterson and Hennessy. This is the only book to care about. All right, so we got to make a decision right now. I just came here to call you nerd. That's fine. I'll take it. I deserve it. You should put a link to your YouTube in your Twitch description. I need to. That's right. I need to do that. I need to make it so that I tweet out with everything and advertise my Twitter everywhere. But guess what? I'm a PhD student and I'm lazy. I'm lazy with this because I got other things to do. I've got to fly out to New Mexico in about a month. And then I got to fly someplace else. Okay, so we got a decision. MIPS or RISC? What do we got? Face cam, please? Don't have a camera. You guys don't need a camera. You guys need full screen architecture. That's what you need. Don't get distracted. You should also post in R Learn Programming. I should, even though this isn't programming. So what do we want? Do we want MIPS or we want RISC? I have both of these open right now. Which are we going to go through? Now I should note that this isn't a web version of the book, so it's exactly like the... Let's see. My stomach hurt. Can you explain why? No. You didn't learn enough computer architecture, so your stomach started hurting. That's why. Okay. RISC. Do RISC because I learned MIPS in class. Okay, so if you already took a class on this, well, it depends. If you took a computer science class, you probably focus more on the software side. The white cover has to be better than the dark cover. I mean, if you like MIPS, it is. Alright, what's the difference between the two? Just the instruction set. One uses MIPS, one uses RISC. A lot of people like RISC because it's new and it's hot. RISC was invented by, it came from Berkeley. I don't know where MIPS came from. MIPS came from someplace. Okay, we're gonna do RISC because nobody said MIPS besides one person that said they already did MIPS. Wait, no. Never mind. Everyone said RISC. We're doing RISC. Do both. I mean, I could teach you both instruction sets, but that would be like learning C and C++. No, it wouldn't. Oh, kind of. There's a lot of overlap between those two. We're doing RISC. We're going into RISC. Do you have a French version of that stream? Of this stream? No, I don't. Because I only speak English and a little bit of German and a little bit of Icelandic. All right, we're going in. We're getting this done. Okay, so if you haven't been to the stream before, welcome to the stream. My name is Engineering Today, and today we're going to learn all about computer organization and design. And we're going to learn that through RISC-V. Okay, so this is a pretty good book. It's good for both computer science and computer engineering people. This was done, like I said, by David Patterson and John Hennessy. I think Patterson is the president of Stanford, and I think, so Hennessy and Patterson are like the presidents of Stanford and another UC system and some UC system school. They're pretty much the most well-known people in computer architecture. I think they've both won the Eckert and Mockley Award, which is like the Nobel Prize for computer architecture. So yeah, pretty cool. So let's see what the book's about. So we're going to go over computer abstractions, a good fundamental thing. Instructions, language of the computer, that's important. If you ever wanted to know what when you compile something, what happens, or this isn't really a compiler thing, but what's actually executed by the processor. That's what we'll learn here. Let's see. Supporting procedures in computer hardware, parallelism and synchronization. A C sort of example, put it all together. Arrays versus pointers, pretty useful. And it even covers some stuff like MIPS and x86. Here's a fun fact. I'll probably say it again when we get to the x86 section. But how long will this take? It'll take however long almost 1,700 pages takes. Listen, I need to change the title of the stream. It's Computer Architecture 101, Part 1. That's what we're at. We're at Part 1. Listen, we're in here for the long haul. Listen, I want you guys learning. What do you think about J. Cole last album? I have no idea who J. Cole is. Oh, fun fact about x86. Did you know that x86 processors don't actually execute x86? The x86 instruction set is actually translated into a RISC instruction set, or yeah. Will the exam after assigned reading? Will this help me my first uni comp sci? It'll help you in computer science. Okay, what is computer architecture? So computer architecture is this great level between software and then the actual physical silicon. Basically, so here's why I like computer architecture. Because if you're deep down there doing stuff on silicon, you don't need to care about software really. You don't really need to care. You just really need to care about your own stuff, your silicon stuff, and you need to look up maybe one level and look at architecture. Now, if you're a software guy, you don't care about silicon, but you maybe care about some architecture. Now, architects is really kind of in the middle. We do those kind of high-level designs, but we have to look at both what's possible on silicon, and we need to look above us in what people are actually doing with software, and we need to kind of take both into consideration. Matt wanted to know about RAM. What is silicon, though? Silicon's an element. Fun fact, though, a lot of chips, fast integrated circuits, aren't made with silicon, though. I think they use, like, gallium arsenide. So, like, yeah, gallium arsenide, and what is it? What's the other one? There's a lot of different ways, because you need a semiconductor, right? And so gallium arsenide works pretty well. That all depends on, like, the energy band diagrams of the elements, or the energy band diagrams of the semiconductors. That's gonna determine, you know, what properties that you can have from that chip. So, like, I think gallium arsenide is used in things like night vision, for night vision applications, and silicon actually won't work there. That's a fun fact for you. Okay. So what else do we have? I skipped over some stuff. All right, so after that, we've got some arithmetic stuff. That'll be pretty interesting. Learn how computers do math. The processor, nice. We're going to actually learn about processors, some basic data paths, hazards. Listen, we're going to figure out that it's absolutely, it almost seems impossible that computers work with everything that they have to take care of. It's going to be fun. The real stuff. We're going to learn about the ARM Cortex-A53 and i7 pipelines. Isn't that neat? We're going to learn what's in some of your guys' computers. Let's see. Okay. Large and fast. Exploiting the memory hierarchy. All right. We're going to learn about memory. Virtual memory. Basic memory topologies. We're going to learn about cache hierarchies. That's going to be fun. Parallelism. We're going to learn about real stuff, too. ARM Cortex-A53 and Intel Core i7. If I'm not mistaken, does Apple use the A53? What does Apple use? I have no idea. I'm trying to think of the reason why they would include Intel Core i7 and ARM Cortex-A53. Pipelines. Sounds like Unix. I mean, pipelines have a lot of different things. This is hardware pipelines. Pipelines is a concept. This is hardware pipelines. You're probably thinking of software pipelines. What book is this? This is Computer Organization and Design, the RISC-V version. I use AMD. Okay. AMD's okay. They have some software problems because they don't hire developers, but, you know, they're okay. They use a lot of the same, I mean, everyone really uses a lot of the same concepts in processors. All of these concepts you'll learn here are, you know, the foundations for all that stuff. What else do we have? Oh, parallel processors. That'll be fun. Does GPU do any pipeline? Of course, you can't get away. If a GPU doesn't do pipelining, that means you have a single cycle processor, and we'll probably see from examples in this book that that's awful. Yeah, GPUs, I need to get permission to do this, but listen, the first ever book on GPU architecture is coming out, and I have early access to it. I'm going to see what I can do. I'm going to see what strings I can pull and see if we can go over that. Because guess what? If we do that, you guys will be ahead of the game. No, this isn't beta testing. This is just preprint. This is it just hasn't been printed yet. The book is done. Listen, I'm not even going to charge you guys. I'm not even going to charge you guys for doing that. We're just going to have a wonderful time, and we're going to learn a lot of great stuff. And I think we're going to have a lot of fun. Okay, so parallel processors. We're going to learn about all of these things, which most of you probably have no idea what it is. SysD, MIMD, SIMD, SPMD, and vector. That's pretty cool. Hardware multi-threading, multi-core, and other shared memory multiprocessors. Introduction to GPUs. Nice. You are already ahead of the game. Listen, if you can take, what do we got here? The NVIDIA Tesla GPU. All right. So you guys know about, the graphics cards that, most gamers buy, and what a lot of the general public buys, right? So what if I told you there's an entire class of graphics cards that don't have a graphics pipeline? They're only meant for general purpose computing. These graphics cards cost 2x, usually 2x plus. Yep, GPU, that's right. They cost 2x plus the highest end graphics card. If you try to get so the most recent architecture is Volta. If you try to get the most recent architecture is the for the GPU from Volta that has a graphics pipeline, the Titan V. The Titan V is about what's it called? The Titan V is about $3,000, right? So the Pascal previous generation, the Pascal Tesla card, the P100, that's minimum price $6,500. That stuff is expensive. That stuff is good. And guess what? I work in a lab, and all I do is work on these cards, and it's so much fun. Okay, and then, we got some appendix stuff, the basics of logic design, gates and truth tables, combinational logic, clocks, flip-flops, SRAMs, DRAMs. I read an interesting paper dealing with DRAMs today. That's pretty cool. DGX2 EZ400K. What's a DGX2? Is that one of the dedicated machine learning boxes where they just shove in a bunch of GPUs? I know at GTC Taiwan, or maybe it was regular GTC, they released some box that has 16 Volta cards in it. And it's just for machine learning computing. Graphics and computing GPUs, nice. This is the stuff I work on. I work on GPU architecture. Okay, somebody asked in another chat, hey buddy, when you mean computer architecture, do you mean programming? Sometimes. This is more architecture. This is more the physical stuff. We'll do some programming stuff on GPUs. But a lot of this stuff there's going to be some assembly level programming that we'll probably go over to understand that, which is good for people that are computer science focused. Because if you write C or Java or something, your CPU is not executing Java or C. It gets compiled down into the instruction set of the processor, if that makes sense. Okay. Appendix D, a survey of RISC architectures for desktop, server, and embedded computers. Okay. Spark, MIPS, Alpha. Oh, this is, ooh, see this right here? This one, the thumb instruction set. Why? This is an ARM instruction set. It has like a combination of 16-bit and 32-bit instructions. Why? Why would you do this? You can also execute assembly directly in C, so it might be useful. Yep, that's true. You can. In fact, if you actually want to, if you care about high performance computing, you generally have to do things like that. There's a lot of optimizations that require you to deeply understand the assembled, the actual assembly level code. And so here's a fun fact from the GPU world. I did matrix mul with AVX. Nice. So here's a fun fact dealing with matrix multiplication. So all the libraries for machine learning that NVIDIA makes to run on GPUs. So we're talking like cuDNN, cuBLAS. So cuBLAS is the linear algebra library. Those are all handwritten and hand-tuned in NVIDIA's hidden instruction set architecture called SAS. Listen, if you don't learn anything about this computer architecture, you've got that fun fact. But hey, I hope we can learn something about instruction set architectures and computer architectures. But guess what? We're going to have fun here. We're going to have fun. All right. So let's see. In praise of computer organization and design, I don't care. Some guy from Xavier, some guy from St. Lawrence. Mark Hill. This guy's a big guy. We'll probably read some papers from him on this stream. Mark Hill's a big guy from Wisconsin-Madison. I probably should know some of these other guys from Northeastern. Dave Cayley. I'm unfamiliar with his work. Same thing with Christos Kozarakis, something like that. Guy from Syracuse. Not sure. Mark Hill's the only person that I really know. All right. Yep. Keep going. Dedication to Linda. Thanks, Linda. It doesn't say who it's from. This was written by Patterson and Hennessy. Who said this? Did they both say it? Did they both dedicate this book to Linda? Are they both in love with Linda? Acknowledgements. iFixit, Chipworks. Listen, you get Intel. You get Intel to give you figures. That's pretty nice. IBM giving you figures. Cray, Apple. That's pretty cool. MIPS, NASA. That's pretty neat. Patterson. The man, the myth, the legend. Okay. About the book. That's okay. RISC-V for this edition. Let's see. Yeah, it's a modern, MIPS instruction, but it offers a simple, elegant, modern take on what instruction sets should look like in 2017. Okay, and it's not proprietary. There's an open source RISC-V simulator. So if you guys, I'll probably look into that. I haven't looked at MIPS or RISC in a long time because, well, I do GPU research, but we'll look into that. We'll see what we can do. We'll see what we can rustle up. All right. Okay. Changes for the 5th edition. Who cares? All right. So if you guys actually, want to tune in and out, or you want to know, who's going to get what from each chapter, you guys need to take like a mental screenshot of this, or you need to take an actual screenshot. I would suggest an actual screenshot. And so this is basically what each of these sunglasses or glasses means. So we got software focus and hardware focus. And then some of them are both, so it's both blue. That means look carefully at this. So like look carefully for both, look carefully for both. But some of these are, completely one or the other, I think. So like right here, hazards and exceptions. You don't really care about hazards and exceptions. Will this be archived on Twitch right after? Yeah, it should be. I have it set up to automatically save VODs. So I hope it does. I'm going to try to upload them all to my YouTube. And if you want to know what my YouTube is, I have to find it. Listen, I can't wait till I pass like the subscriber threshold on YouTube, where I no longer have this enormous link that doesn't even say my name in it. When I can get youtube.com/channel/engineering today, that's the dream. But until then, this is what we have to deal with. Okay. So let's see. All right. So we have this. Let's see. Instructor support. I don't need instructor support. I am the instructor. Click the bell. Click the bell. I don't know what the bell is. I guess the bell is probably like follow or something. Listen, just smash that sub button. I would suggest not smashing that sub button because it doesn't exist yet. There is no subscribe button as of yet. Maybe someday. Maybe someday we'll be there, but today is not that day. We'll get there. But guess what? It's not about subscribers. It's not about donations. Listen, just like I said and showed at the beginning of this stream, I just want you guys to learn something new. Listen, we just want to learn something new today. That's all we care about. We just care about learning something new. Okay, let's skip all this. We got a lot of thanks. Look at all these people that contributed to this book. That's a lot of people. Okay, do I know any of these people? Maybe. There's a lot of people here I don't know, though. David Wood. David Wood's also another big guy. He's a big guy in computer architecture. He's from Wisconsin, Madison. Same place as Mark Hill. Okay, and then the guys that wrote or that converted everything to RISC-V. Nice. Too many cooks? Nope, never enough cooks. All right, here we go. We're starting. We've made it. Computer, abstractions, and technology. Okay. So what are we going to do in this chapter? Let's see. Let me get my cursor thing. So we're going to look at some information on cost performance of computers. Let's make that a little bit bigger. Let's see. Yep, they're going to be much better than they are today. And then to participate in these advances, computer designers and programmers must understand a wide variety of issues. That's true. We're going to see that we need to really, really be cognizant of current technologies, where technologies are headed, and that's why I think it's really important that I present some research papers on this stream, because we're never going to advance if we don't, look to the future. We can't just, learn what everyone before us learned. We have to, cut that off at some point and move to the future. So while this chapter focuses on cost, performance, and power, it emphasizes that the best designs will strike the appropriate balance. That's true. So what happens if we have a memory-intensive application, a cache-sensitive application, and a compute-sensitive application, and we have some processor to design? Now, a compute-sensitive application is exactly what it sounds like. It puts pressure on the number of compute units you have. So the more compute units, the better. A memory-intensive one, it's going to soak up a lot of those memory channels in a processor. And then a cache-sensitive one, it's really going to put the cache to the test, and it might thrash the cache. So better cache is better in that sense. So, we could design a computer that's really, really good for cache-sensitive apps. We could make this giant cache. We can make this a really big cache. But we're not helping out memory-sensitive applications, and we're also not helping out compute-sensitive applications. So that's what it means, but we have to strike this balance. So these are just keywords. We can skip over that. Outline. Nice. Okay. Welcome to the book. Welcome everyone to the book. Book, say hello. Chat, say hello to the book. Okay. So let's get right into it. Let's see if there's anything interesting here. So, yep. We're an economy that has become dependent in part on the rapid improvements in information technology promised by Moore's Law. And we'll go into Moore's Law in a minute. This unusual industry embraces innovation at a breathtaking rate. And we're going to see that with Moore's Law, of how amazing that computers are. One of my professors had this great example, and I can't remember the exact figures of it, but it was comparing the automotive industry to Moore's Law. And if the automotive industry had scaled the way Moore's Law scaled, we'd be driving cars that cost pennies that get, hundreds of thousands or millions of miles per gallon. That's the kind of scaling we're talking about, and innovation that we've seen with computers over the last, since the 1940s, really, when this came about, and more along the lines of when the first transistor came about. So let's see. The race to innovate has led to unprecedented progress since the inception of electronic computing in the late 40s. This was the paper we read from John von Neumann talking about EDVAC, the first stored program computer that was designed and built by Eckert and Mauchly. Here we go. Had the transportation industry kept pace with the computer industry, for example, we could travel from New York to London in a second for a penny. Now, just let that sink in for a little bit. That's the level of improvement we're talking about. This is why it's such a great time to get into computer architecture. It's so fast moving. There's so much innovation going on. This is why I love it. All right, so let's see. Take just a moment to contemplate how such an improvement would change society. Living in Tahiti while working in San Francisco, going to Moscow for an evening at the Bolshoi Ballet, and you can appreciate the implications of such a change, right? Think about it. Think about when computers became a household item. Think even more recently for smartphones. Look how fast smartphones became. Everyone has a smartphone now, or at least that's the impression. It's such a common thing now, which didn't exist early 2000s. No one had one. Your fridge is smart. That's right. That's right, Robbie. It is smart. It probably has, connects to Bluetooth. My phone has a gaming mode. Absolutely. There's all kinds of crazy stuff that happens now, and it's just started existing because we can make transistors at, production level. We can make it at 10 nanometers now. They can even make smaller transistors, not at production scales though. I think they've made 7 or maybe even 5, but not in a production scale. Like you're not going to, so I think the NVIDIA Volta GPU has like 21 billion transistors or something. You're not making a 21 billion transistor chip in 5 nanometer tech yet. Your yield would be 0. You would get no chips out of production. Okay. Computers have led to a third revolution for civilization, with the information revolution taking its place alongside the agriculture and industrial revolutions. This is true. See how fast things have moved as far as, data science. How many job titles do you see of data science nowadays? A lot. There's a lot of data scientists out there now. Okay. Let's see. So another amazing thing. So it really enables a lot of fields. Astronomy, biology, chemistry, and physics. These only exist. A lot of the advancements in these fields are only possible because computing has got to where it is. There's a lot of problems that were previously unsolvable that because of compute, we're able to, if it was too hard to come up with a clever solution, we can just iterate through all possible solutions or all possible inputs for something and find the solution that way. That's the point that we're at. MRI is pretty dependent on computing too, I think. Listen, anything that has a circuit board in it is dependent on computing, because that motherboard was designed with a computer. So let's see. The computer revolution continues. Each time, the cost of computing improves by another factor of 10. The opportunities for computers multiply. Applications that were economically infeasible suddenly become more practical. So machine learning is a very interesting one to consider here. So a lot of people don't know this, but machine learning, it actually came into existence, I think, in the 40s or 50s, right? 1940, 1950. That's when machine learning came to fruition and existed, and then it died away. And then I think in the 70s or 80s, there was another revolution where there was more work into machine learning. And then after that, today is the third, and this one's here to stay because we finally have the compute to make machine learning viable. Okay. Computers and automobiles. Until microprocessors improved dramatically in price and performance in the early 1980s, computer control of cars was ludicrous. That's right. Way too big, way too power hungry. Today, computers reduce pollution, improve fuel efficiency via engine controls, and increase safety through blind spot warnings. Most electronics, or all electronics, are controlled by some brain within the car. Cell phones, the Human Genome Project, that, it was a neat idea, but it didn't end up being as revolutionary as people thought, I don't think. The World Wide Web, yep, the internet is only possible because of computing. And search engines. Listen, everyone likes Google. Everyone likes how you can, search up anything. And oftentimes, and Google presents you exactly what you're looking for. That's great. So let's see. Traditional classes of computing, applications, and their characteristics. Although a common set of hardware technologies is used in computers ranging from smart home appliances to cell phones to the largest supercomputers, these different applications have distinct design requirements and employ the core hardware technologies in different ways. Broadly speaking, computers are used in three dissimilar classes of applications. Okay. So we have personal computers, which is something that everyone is probably familiar with. We have servers. So let's see what they say about PCs first. So, as we all probably know, they emphasize delivery of good performance to single users at low cost. So it's not going to be your highest performance, but it's going to be, some of the most cost-efficient performance because it's meant for the general market. This class of computing drove the evolution of many computing technologies, which is nearly 35 years old. Yep, that's true. So I guess it's been around 35 years now since the PC revolution, really started to take over. So that's pretty cool. I like that. So let's see. Servers. So most people are familiar with servers as well. So they're the modern form of what were once much larger computers and usually accessed only via a network. So, Amazon, for instance, with cloud services, they rely on servers. Microsoft Azure, they rely on servers. So, let's see. Did they say anything interesting here? Servers are built from the same basic technology as desktop computers, but provide for greater computing, storage, input-output capacity. In general, servers also place a higher emphasis on dependability. So when we get into servers, later in the, I don't know if they go over it in this book, but in the next computer architecture book that we're going to go over, we'll probably talk about RAID, which stands for Redundant Array of Independent Disks, and we'll learn about how exactly servers provide such dependability and fault tolerance. That's a really interesting area. I'm actually getting into the fault-tolerant computing world a little bit in my research. I'm at least looking into it for GPUs. It's a very interesting field. Okay. And then we have... Okay, so we're still in servers. So supercomputers are, another form of servers tied together. Processors, so they have many terabytes of memory and, petabytes, probably yottabytes of storage. Because we want to store everything nowadays. Everything, just save it all. I mean, the most amazing example is something like Twitch or YouTube, where they will just take your video and they will just store it. And, I recorded a video the other day, about 45 minutes, and it by itself was 2.1 gigs, and that has to go someplace to get stored in YouTube's cloud, and they just do it for free. So it's truly an amazing, amazing time. So here we have a little bit on kind of the number systems that we're going to see. So there's often the confusion of these two number systems, because sometimes people will use them. Yeah, of course it's compressed. Yeah, of course. But if you think about the amount of videos that get stored, it's still an insane quantity. So, generally when we're talking about binary, we do 2 to the power of 10. So, if someone says 1K or 2K, or they say a meg or a gig, most of the time they're probably referring to the base 2 number. They're probably referring to 1K is generally 2 to the 10th, which is 1024. Or if so it generally will, people try to use these interchangeably, but most of the time when we're doing sizing, we're using the base 2 number. Okay, so let's see. So then we have the last one, which is the most low cost, which are embedded computers. These are the things that are everywhere. There are microprocessors, everything that makes IoT possible, basically. So everything that has a little bitty chip in it that controls something, these are microprocessors. Embedded computing, if you have a smartwatch or something, these are all embedded systems. Okay. So let's see. Anything else interesting here? Despite their low cost, embedded computers often have lower tolerance for failure, since the results can vary from upsetting to devastating. So if you think about something like a pacemaker, right? So if your computer messes up, okay, that's bad. We don't want that. We might lose some data. That's pretty bad. If a pacemaker messes up, that's a little bit worse. Someone's life hangs in the balance, or some medical equipment that use embedded computers or little microprocessors. We don't want those messing up. Okay, so let's see. Welcome to the post-PC era. This is an interesting thought. So the continuing march of technology brings about generational changes in computer hardware that shake up the entire information technology industry. Okay, replacing the PC is the personal mobile device. Most people don't need a computer anymore. So they have a computer at work, maybe, or maybe they don't. If you have a service job, it's very likely that you don't need a computer for a lot of things. And most people, what they use technology for is personal media, or they use it for personal entertainment purposes. So social media, Netflix, YouTube, Twitch, etc., etc. So you don't really need a PC for that anymore. Something like an iPad or a tablet or a smartphone will work just as well. So, we're in this age now where, the markets are shifting a lot. And one of the things that a lot of manufacturers of PCs are dealing with right now is that personal computer sales they're drastically decreasing, and companies like HP and Dell and Lenovo, they don't make anything off of hardware. Nobody makes anything off of hardware. If anyone thinks that some company is getting rich off of selling laptops, they're not. Nobody makes money off of hardware. What they make money off of is services to support that hardware. They make all their money on the warranties or the service support packages, which is mainly from selling things like servers. You don't make money on the hardware from selling servers to companies or to data centers. You make money on selling the 3-year, 5-year support plan for the servers that you sold them. That's where all the money comes in from. Okay, so here we have a pretty interesting graph. So this goes up to, 2012. And so we see that, despite what some people think, non-smartphones a lot of money is still being shoved into phones that are not smartphones, which are, they're just about at $1 billion now, decreasing, but still just about at $1 billion. Smartphones increasing, just past 600 million in 2012-ish. PCs, not including tablets, very slow rise. Tablets are increasing, not as high as smartphones, but looks about 2 to 3 times faster, or maybe about 2 times faster than PCs. So that's fairly interesting. I had no reference really for tablets. Okay. So yeah, PCs isn't declining, but it's definitely not growing very quickly. And it's even, one could argue that it seems like it's at least slowed down from this 2009, 2010 upward trend. Okay. Taking over from conventional server is cloud computing. Yep. This relies upon giant data centers that are now known as warehouse scale computers. So Amazon, Google build these warehouse scale computers containing 100,000 servers. Very interesting stuff. Things like software as a service. So you basically build the software, and instead of companies having to design their own software for a specific task, someplace will just say, hey, we'll sell you a template of ours to use for you to use. So that's pretty interesting. Today's software developers often have a portion of their application that runs on the, I think this is personal mobile device, and a portion that runs in the cloud. That just makes sense. So this is kind of where the market's going, as we see from here with smartphones. So, smartphones are still very limited in size, and there's so many things that go into designing a smartphone. You have to consider your battery size. You have to consider the performance you're going to have and quality of service for the number of apps you're running and you have to consider things like, even thermal is so important. You don't want your phone to get burning hot. So that's very important. So let's see. What can you learn from this book? Or what you can learn from this book? Chat, this is you. This is what you're going to be learning from this book. Successful programmers, listen, if you're a programmer, this is it. This is what we've been waiting for. We're here now. We're here. So let's see. What are we actually going to learn from this book? So, 60s and 70s, constraint on computer performance was the size of computer's memory. So what we wanted to do back then was minimize memory space to make programs fast. In the last decade, advances in computer design and memory technology have greatly reduced the importance of small memory size in most applications other than those in embedded computing systems. Okay, here we go. Here's what we're actually going to learn, these bullet points. So 1, how are programs written in a high-level language? And how does the hardware execute the resulting program? So this is going to go from that high-level abstraction. And then we're going to see what happens on the instruction side. I can finally unroll my loops? Absolutely. Doesn't MPI just have a... Can't you just do like pragma unroll and it automatically does loop unrolling for you? I'm pretty sure you can just do that. Also, most compilers probably do that for you automatically. If the compiler is smart, it should. Okay. So let's see. Next thing we're going to learn. The interface between the software and the hardware. Okay. Pretty interesting. We're going to learn what determines the performance of a program, and how can a programmer improve the performance. This is going to be a very interesting part. How does knowing the architecture of the platform you're working on influence how you write your code? That's going to be very interesting. That's something that interests me a lot. It's very relevant in the GPU space. Let's see. We're going to learn what techniques can be used by hardware designers to improve performance. So we're going to learn on the hardware side how we can improve this. And then this is the advanced book. This is the book we're going to do after this book. Computer Architecture, a Quantitative Approach. This is where you really start to learn about modern computer architecture. It's very interesting. Then we're also going to learn about energy efficiency. We're going to see why that's so important, especially in the modern era with transistors being so small now. We're going to see the shift from sequential processing to parallel processing with multi-core processors. And we're going to see what impacts that has on the architecture and why this seems like magic once you start to learn how this works. Things like consistency in memory. It's, when I first learned this, all I could think to myself was, how does any of this actually work? It doesn't seem like it should be possible. Okay. And then we're going to see, since 1951, what great ideas did computer architects come up with and lay the foundations of modern computing. So we're gonna really see the history of computer architecture and the logical steps that took us from where we were with EDVAC back in 1945, 1946 when it was completed, to today, where we have these massive chips with billions of transistors that can crunch data faster than somebody in 1945 would have ever thought was possible. It's going to be really, really great. All right. So let's continue on. So, okay. So they're going to go over a couple things. So there's a lot of words that we'll go over, and we want to make sure that everyone understands what these mean. So BIOS, CPU, DIMM, DRAM, PCIe, SATA. I actually took an entire course that was on a protocol like SATA. It's called SAS. It's what data center hard drives. So here's something. Brief side note. Data centers don't use SATA drives because SATA drives are awful and they have no redundancy. So usually the most cost-efficient balance between performance and cost is something known as SAS, which stands for Serial Attached SCSI. And SCSI stands for it's SCSI, I think. It's like Serial Computer Systems Interface. Basically, it's a dual-ported drive that has some failover. Okay. Oh, they even define what an acronym is. Isn't that nice? Okay. So let's start out with talking a little bit about program performance. Yep, nested acronyms. Listen, there's so many acronyms that are horrible. I think SAS is one of the worst because it's an acronym within an acronym. Let's see. So you can't get this book anywhere for now? No, that's not true. You can get this book everywhere right now. The GPU architecture book that I was referring to isn't out yet for publishing. It doesn't exist. I have a pre-release PDF of it that has a password. I think it's getting published sometime this year, but it's definitely not out for sale yet. Okay. Leak it? No, I'm not going to leak it. I know some of the people that wrote the book. I'm not going to leak the book. How do you think I got access to the book? I didn't just contact the publisher and ask if they have any books that have been released yet, and they gave them to me. Understanding program performance. The performance of a program depends on a combination of the effectiveness of the algorithms used in the program, the software systems used to create and translate the program into a machine instructions, and the effectiveness of the computer in executing those instructions, which may include input-output, I/O. So let's talk about this a little bit. So we have the algorithm. So the algorithm is going to be what a computer scientist has come up with. This is going to be or maybe even a mathematician has come up with, and it will be a way to solve a problem in it's a programmatic way to solve a problem. And then after that, we have the programming language, compiler, and architecture. Now, it may seem a little confusing right now of why we have architecture and compiler in the same box. But it's really impossible to have these two separated, because what happens is you write a program, it goes to the compiler. What the compiler does is the compiler will translate that language that you wrote the program in, so like C, and it will change that into the underlying architecture. So if you're on an x86 processor, it's going to translate it into the x86 instruction set. And it's going to do whatever optimizations are built into the compiler. And there's a lot of crazy stuff that compiler people have worked on to make that really, really good. So then after programming languages and compilers, there's, of course, the processor and memory system. So this is when your code is running on the processor. That's where we are at this point. And then following that, here, let me go ahead and full screen this. I don't know why I haven't full screened it. So following that is, of course, the I/O system, hardware, and the operating system. So this is a little more abstract. This is going to be, the human interaction or maybe some other device's interaction with your computing system. And it's also how the software is interacting with this computing system. And so, this is going to determine how fast I/O operations may be executed. So, So we're not going to cover algorithms in this book. There's a great book by Corman, Lyserson, Rivest, and Stein called Introductions to Algorithms. Maybe we'll go over that. That'll be interesting for the computer architects and computer science people alike. Maybe we'll go over that sometime. So, to demonstrate the impact of the ideas of this book, we improve performance of a C program that multiplies a matrix times a vector in a sequence of chapters, a matrix vector of multiplication. Nice. So, we're going to talk about data level parallelism, and using subword parallelism via C intrinsics, we can get the performance over the baseline to improve by 3.8x. That's pretty good. Not the best, but still pretty good. So when we do instruction level parallelism, or ILP, that's when we'll do loop unrolling to exploit multiple instruction issue and out-of-order execution hardware. If you guys didn't know, Meltdown, the security issue, is a result of out-of-order execution hardware, and we'll improve it by another factor of 2.3. So keep in mind, this isn't 3.8 or 2.3. This is 3.8 and 2.3. In the category of memory hierarchy optimization, so this is just looking at the memory subsystem, we're going to use cache blocking. I think this is the same. I think cache blocking just means the same thing as tiling, and we'll go into what that is. To increase performance on large matrices by another factor 2 to 2.5. And then finally, we're going to use, in the same level as, so we're going to use thread level parallelism, or TLP. We can use parallel loops in OpenMP. So I would prefer CUDA. To exploit multi-core hardware to improve performance by another factor of 4 to 14. So we're getting this huge jump in performance here over time. So this is going to be really interesting to see because we're doing the same application for all of these. So let's see. So check yourself. Sections are designed to help readers assess whether they comprehended the major concepts introduced in this chapter. So the number of embedded processors sold every year greatly outnumbers the number of PC or even the post-PC processors. Can you confirm or deny this insight based on your own experience? All right, chat. This is your first question, and there are no wrong answers here. Except there is. So can you confirm or deny it? Listen, I'll say that I can confirm it. You see so many people now with smartphones, and many people are, I think there was the, what was that Apple commercial that a bunch of people got mad about because, it had the girl in it that, somebody asked, is that a computer? And she said, what's a computer, right? There's that commercial that everyone got angry about. But, in some sense it's true. And we actually have some data in this chapter that proves it, right? So, we've got some interesting, that's an interesting point that's being made here. How does it compare? Let's see. Try to count the number of embedded processors in your home. Listen, like all good research papers, I leave this as an exercise to the audience. Okay, so let's move on to the second one. As mentioned earlier, both software and hardware affect performance of a program. Can you think of examples where each of the following is the right place to look for a performance bottleneck? Okay. All right. The algorithm chosen. Can you think of examples where each of the following is the right place to look for a performance bottleneck? Okay. So clearly, the algorithm chosen can be an issue. So this is so every algorithm has a different cost related to it, and they have different orders of performance. One of the easiest ways to think about this, time complexity is a great, it's a great way to think about the algorithm chosen. But there's a subtle thing. If you want to think more like an architect, when we're thinking about the algorithm chosen, we need to also think about the platform that we're working on. So if we're working on a CPU, we have to keep in mind that CPUs are, they're not very parallel compared to a GPU. So when we're optimizing an algorithm, to run on a CPU, a lot of times we're optimizing its serial performance. And when we do that, oftentimes we wind up with an algorithm that doesn't work as well with, or we wind up with an algorithm that doesn't work as well on a GPU. In fact, I'm trying to remember exactly. So there's iterative methods for solving matrices, right? For solving systems of equations. So there's a very classical way of solving systems of equations iteratively that was all but forgotten for the longest time. And the CPU community worked for a long time and created a great serial solution to the problem. And I'm going to see if I can find that real quick. But one of the interesting things is now with the mass adoption of GPUs for general purpose programming, that old application that wasn't as good serially, turns out the serial one you can't parallelize. But the old one that had worse performance on CPUs it's a term that a lot of GPU people like to use, embarrassingly parallel. So let's see, iterative method solve linear equations. Let's see if I can find what this was. I won't look too hard. If I can find this quickly, it'll be fine. Actually, I know exactly where to look. I can look on this site. I can see if it's still here. Okay, it's still here. Here we go. So the Jacobi iterative method. The Jacobi iterative method was a means a long time ago of solving systems of linear equations iteratively. However, it got replaced by another. Let me see if let me pull it up on stream. So, okay, here we go. So there's two different iterative methods here. So there's, of course, the Jacobi iterative method, and so that's this one right here. And it's this iterative method that you can make extraordinarily parallel, and it works absolutely wonderfully on GPUs. The Gauss-Seidel or Gauss-Seidel method, I don't know how to pronounce that. That method is not parallelizable at all. It's great for serial performance, and so it works great on CPUs, but it doesn't work great on GPUs. So there's a quick example for you of the algorithm, and I spent way too much time on that. So the programming language or the compiler. So of course, depending on your application, you really need to look at the compiler for what you're doing, and you need to look at the optimizations that your compiler is doing, maybe even look at the assembly itself. The operating system, so there's going to be some operating system overhead. There's a lot of research papers that go into this and understanding how something like the TCP/IP stack actually, incredibly can get in the way of communication, or that it can really slow down and make communication overhead a bottleneck for NIC processing. I think there's an entire paper that I read on that a while ago. I don't do a lot of NIC stuff, so I don't remember it, but the processor. So here's a fun fact. If we go back to the Pentium days, and we look at something like, if we look at Pentium 3 versus 4. So Pentium 3, I think, was 750 megahertz, and then Pentium 4 was like 1 gigahertz, right? So you would think, Pentium 4 wins. Yay. Wrong. Pentium 4 was slower than Pentium 3 because Pentium 4 used something ridiculous like a 24-stage pipeline, while the Pentium 3 only had like a 10-stage or 12-stage pipeline. And pipelines have diminishing returns, so they added so much overhead here that even though it had a 1 gigahertz clock, the 750 megahertz processor was better. And then the I/O system and devices. So clearly, if we have some I/O device that's very slow, we can see that it could cause a bottleneck. So you can think about a USB drive. So if we have a USB drive and we're trying to copy data, clearly if we get a better USB drive that has a has a high, it can take a higher bandwidth, it has a better buffer inside of it for the data transfer, it'll be better. Now there's also the limitation of USB and whether or not it's the actual USB interface that is the limit. But it's very interesting. Okay, any questions on any of this stuff so far? Or else we'll continue going to the 8 great ideas in computer architecture. SATA versus M2. What's M2? I know what SATA is. SATA versus M2. Let me look it up. What's M2? Is that I'm guessing by the interface. Let's see. Are all M2 drives NVMe? No, M2 is just a form factor. So I don't think that's a very good comparison. This is just from what I'm looking up, but it says M2 is a form factor. It's not a protocol. SATA's a protocol. Okay. NVMe is also not NVMe is also not a protocol. NVMe is non-volatile memory. So it would be how it's connected. So if you want to make the comparison, it would be something like SATA versus PCIe versus USB versus SAS versus SCSI. All of those are communication protocols, but it's you can't compare something like NVMe, which is a type of memory, versus a protocol. Okay. So, moving on. 8 great ideas in computer architecture. So, we now introduce 8 great ideas that computer architects have invented in the last 60 years of computer design. These ideas are so powerful that they have lasted long after the first computer, probably referring to EDVAC. These great ideas are themes that we will weave through this and subsequent chapters as examples arise. Okay, so we're going to go over 8 themes, and it's going to be, exactly, how most computer architects think and what we keep in mind when we look at new ideas. And maybe I'll try to impress this more when I go over something like a research paper. Okay, so let's see. Number 1, design from, oops, that's not right. Let's get that highlighter. Okay, so 1, design for Moore's law. So the one constant for computer designs is rapid change, which is driven largely by Moore's law. It states that integrated circuit resources double every 18 to 24 months. And I don't think it says it here, but I think it also price decreases by 1/2. I think that's the whole idea. So this is a very interesting thing. So let's take a second to think about what this means. So this means that we get twice as many transistors to work with every 2 years. Now that's crazy. So when we talked about, going from, I think it was like California to New York in a second for a penny, this is why we've had such amazing change. It's all because of Moore's law. And keep in mind, Moore's law isn't like a strictly defined equation. This is just a trend or a pattern in computer architecture that just happens to have persisted over the past, 40 years or so. It resulted from a 1965 prediction by Gordon Moore, one of the founders of Intel. And I think before that he was at Shockley Labs. If you know anything about electrical engineering, you probably know that name from the Shockley diode. So the resources available per chip can easily double or quadruple between the start and finish of a project. Like a skeet shooter, computer architects must anticipate where the technology will be when their design finishes up rather than where it starts. Okay. So this is a very interesting concept because from here we can understand that we have to plan for the future, and that future comes very quickly. And so we have to make designs that are one of the most important things is making designs that are scalable. We need a design that not only works at the current technological generation, but we need a design that can span multiple generations. Okay. Any questions on Moore's law before we move on? Also, I think this is a good time to take a little, let's see. Oh, there we go. We got something. Isn't Moore's law falling off? Absolutely. Moore's law is falling off. So the easiest way to see that is with frequency scaling. So we used to see in the same thing as the doubling of number of resources, we also used to see doubling of frequency per generation. But now we've noticed we've saturated around 3.5, 4 gigahertz. And it's likely that we won't be able to get much more just in frequency scaling wise, because of that, because of physical constraints. So a lot of people are predicting that 5 nanometer is as small as we can possibly get. 7 nanometer is something that's being worked on right now. Between I know Xilinx and Intel are working on that together right now to path to 7 nanometer technology. And even Intel itself is having trouble getting to producing large chips at 10 nanometer. They're not getting the yields that they would like at 10 nanometer. I think even the Volta architecture, I think Volta was originally planned to be 10 nanometer technology. They didn't quite get there. I think it's 14 nanometer technology. Okay. So moving on. Let's see what we got. So, using abstraction to simplify design. So this is our next key concept. Both computer architects and programmers had to invent techniques to make themselves more productive, for otherwise design time would lengthen as dramatically as resources grew by Moore's law. So we need ways of designing things where we don't get stuck in the weeds, We need to be able to see the path forward and, hide some of the low-level nitty-gritty details that would otherwise get in the way. And so we do that by abstractions to characterize the design at different levels. So, if you're a Canyon Lake? I don't know what generation. I don't remember what all the generations are. Is it Coffee Lake the newest architecture? I think Coffee Lake is the newest. Okay. We'll use abstract painting icon. So this is going to be, when we're talking about abstraction, you're going to see this little graph in the book when it's something related to Moore's law. So make the common case fast. This is Amdahl's law, and we'll go into Amdahl's law later. So we can think of it this way. This is the easiest way, or one of the easiest ways. If we have a car, and somebody says, if we put the best wheels on the car, we're going to go 5 miles an hour faster. But if someone says, okay, if we put a new engine in the car, we'll go 70 miles an hour faster. Which do you think is more important? If your only concern is speed, which in many cases for architecture it is. You're probably going to care about the engine more. So in this case, we want to optimize for the common case, which is going to be not only which part of the architecture is being used the most, but also something such as what is the program doing. So, so those are kind of tied together, right? So if the program is very memory intensive, that means we're going to be spending a lot of time in the memory subsystem. So we should probably focus on making the memory subsystem fast. So we need to find out what the general trend is, and we need to optimize it. And then once we've done a lot of optimization and we're running out of design space to look at, we can come back to some of the other ways. So after we've put the new car engine in, and maybe we've put a lightweight frame on the car, then we might go, okay, so what can I still do to make my car faster? And then we put on the tires, the new tires. They'll make us go 5 miles an hour faster. So this common sense advice implies that you know what the common case is. So this is often true because we can find out the common case through benchmarking. And so that's what they mean by careful experimentation and measurement. So they actually use a sports car. Okay, so they use a sports car. So they're trying to make the same analogy that I was. That's interesting. I promise I didn't steal it from them. I've never read this book. I used a different book when I learned computer architecture. So this is a new experience for me, reading this. So, performance via parallelism. Since the dawn of computing, computer architects have offered designs that will get more performance by computing operations in parallel. We'll see many examples of parallelism in this book. We use multiple jet engines of a plane as our icon for parallel performance. This is the worst picture I would have picked for parallelism. Really? The best thing you'd come up with is an airplane? What? No, I don't believe this. They use an entire airplane because of engines. What? That doesn't make any sense. This makes sense, making the common case fast. You got a speedy race car. This makes sense. It's abstract art, abstraction. Moore's law, it's doubling. So you've got a linear graph. Why would you use... Okay, we're going to move on from this. That's slightly frustrating. That's okay. Okay. So performance via pipelining. I bet all the other ones make sense except for parallelism. Okay. So performance via pipelining. A particular pattern of parallelism is so prevalent in computer architecture that it merits its own name, pipelining. Okay. For example, before fire engines, a bucket brigade would respond to a fire, which many cowboy movies show in response to a dastardly act by the villain. Townsfolk. Okay, so a bunch of people carrying water to the source of the fire, passing buckets down, as they could much more quickly move buckets up the chain instead of individuals running back and forth. So that's what we mean by pipelining. We mean that every single step of a processor is going to be doing a different thing, and they're not going to be relying, on the previous step or the next step. Now, that's not entirely true because you're going to have dependencies where things are going to rely on different stages. But we're going to see that there's a lot of ways to overcome that through things like instruction reordering, and the worst case, we're going to have to stall the processor. But a lot of times we can get past some of those issues. So, performance via prediction. Following the saying that it can be better to ask for forgiveness than ask for permission. So, if you're a Python programmer, you know that pretty well. The next idea is prediction. In some cases, it can be faster on average to guess and start working rather than wait until you know for sure. So, here's a fun fact. So you know how we talked about earlier that out-of-order execution is the reason why Meltdown exists, the Meltdown security vulnerability? So prediction and speculative execution is the reason why Spectre, that vulnerability, exists. So there's another fun fact for you, if you didn't already know that. This is of course assuming that the mechanism to recover from misprediction is not too expensive and your prediction is relatively accurate. So this means that, okay, we need to be able to predict things fairly well, and then when we have to roll back if we did something wrong, it has to not cause too many problems. And look, prediction, it's a crystal ball, it makes sense. So hierarchies of memory. Okay, so let's see. Programmers want the memory to be fast, large, and cheap. As memory speeds often shape performance, and we'll see that memory scaling has been horrible compared to performance-wise, compared to the performance of and frequency of a processor. Architects have found ways they can address these conflicting demands with hierarchy of memories. That means we have memories that handle different tasks. So we have parts of memory that are geared more towards very very fast response, and then we have other parts of memory that deal more with massive, or that with more bandwidth concerns. So sometimes we just want something quickly, sometimes we want to make sure that a lot of things can be captured. So as we'll see in chapter 5, caches give the programmer the illusion that main memory is almost as fast as the top of the hierarchy, and nearly as big and cheap as the bottom of the hierarchy. And so they use this triangle because most of the time when we're talking about caches, we're referring to this top as being the L1. So oftentimes this is written with a $sign. So this will be the L2 cache, and this will either be the L3 cache or the last level cache. Okay. So what's next? Dependability via redundancy. So this is going to be especially important when we're talking about servers, but it's also important with just computers themselves because memory has issues. You have to refresh memory. If you store something in memory, it can't just stay in there forever after it's been written once. It's going to have to be refreshed at some point, or you're going to lose that data. And that's part of fault-tolerant design, is that you prevent things like crosstalk, where there's a capacitive coupling between physical locations in memory that can cause bits to change, which is very bad. So computers not only need to be fast, they need to be dependable. Since the physical device can fail, we make systems dependable by including redundant components. So this is important. That can take over when a failure occurs and help detect failures. So things like exceptions. We use the tractor trailer as our icon, since the dual tires on each side of the rear axles allow the truck to continue driving even when one tire fails. So this makes way more sense than the airplane still. I'm still angry about the airplane. Okay. So now we've got what our main core ideas for architecture are going to be. It's going to be designing based on Moore's law. It's going to be looking at abstraction to give us, ways of breaking down different levels of design into manageable bite-sized pieces. We're going to try to focus on the most important parts of making good architecture first before we do the minor optimizations. We're going to find ways to exploit all the parallelism we have to increase performance. We're going to use pipelining to make sure that everyone's doing something at the same time. And then we're going to use prediction in order to compute things ahead of time so that we don't have to, we're not waiting around for data. And then we're also going to focus on having hierarchies of memory in order to fulfill this need of fast, large, and cheap memory spaces that programmers want ever so much. And then we're going to focus also on dependability via redundancy, so that if a problem happens in the processor during execution, we don't lose everything that we're working on. Okay. One second, I need to respond to a message. Okay, and I'm back. How's everyone doing? Everyone still doing well? How's everyone doing this lovely Friday evening? Or Friday morning? I don't know where everyone's from. How's everyone doing today? Livestream Sniper, pretty good. That's pretty good. 2 a.m. here? Oh man, that is late. Does that mean UK-ish area? It would be Saturday morning? Alright, Saturday. Nice. See, it's 9 p.m. Listen, I'm in my lab at 9 p.m. We're having a grand old time in the lab. Okay, yes, UK. Very nice. I had something accepted into a conference that was in Belfast a couple months ago. That was pretty neat. 3 a.m. All right, nice. That's going to be a little further over. That's going to be, what, GMT -1? Okay. So what did everyone have weekend plans? Anyone have anything fun going on this weekend? Okay, Denmark. Gotcha. Very nice. I've always wanted to go there. I was thinking about going there for my honeymoon. Either Denmark or probably make a first stop in Iceland because it's so cheap to go there. So what is everyone doing this Saturday or Friday evening, besides learning everything that there is to know about computer architecture? That's always fun. That's why I'm in my lab on a Friday night. Sitting at home all day? Hey, nothing wrong with that. I've had those days. See, I can't say that, I'm not. I can't say that, I'm doing something else, because I'm literally just sitting in my lab all day. Basically what happens is I work out at home in the mornings, and then I sit in my lab, and then I go home at around midnight. That's my life. Listen, I'm not complaining. I love everything that I do. And being able to teach stuff like this, it's a lot of fun. I enjoy it. Okay, we can go ahead and continue on then. So let's see. What else do we have? What else are we working with today? So, below your program, a typical application, such as a word processor or large database system, may consist of millions of lines of code and rely on sophisticated software libraries that implement complex functions in support of the application. As we will see, the hardware in a computer can only execute extremely simple low-level instructions. To go from a complex application to the primitive instructions involves several layers of software that interpret or translate high-level operations into simple computer instructions, an example of the great idea of abstraction. So with something like that, we're talking about compilers. Compilers and the instruction set architecture. Okay, so moving on. So figure 1.3, I guess we'll see it down here, shows these layers of software organized. Okay, we can just skip this. So this is basically what we're talking about. The different levels of abstraction that we have. So we have, at this very high level, we have the application software. So this is whatever app you're going to be running on your computer. When you write an app, as, I'm sure some people in here that are computer science focused have done before, you don't care really about what's going on at the hardware level. You can really just kind of worry about, okay, where's my hooks, or where do I plug in to the operating system? So then that leads us to system software. So system software, once we start getting more into things like operating systems, we have to kind of look above us. They have to look above themselves and go, okay, so what are these applications that are surrounding me trying to do? How do they hook into me? And then what are they trying to accomplish? And so with this, they have to have, system software itself has to have hooks into the hardware. They have to know how to speak the language of the hardware in order to calculate things and get those results back and push them back to application software. So of course, this is a simplified view. You could, throw in some extra layers here and there depending on, what your focus is. But in general, this is about as much abstraction as you probably need. So among the most important, so an operating system interfaces between a user's program and the hardware. So like I said, we're talking about operating systems at this level. And then this is some application, and then of course this is just the hardware. So examples of operating systems, so Linux, iOS, and Windows. Okay, so we know what operating systems are. So compilers perform another vital function, the translation of a program written in a high-level language, such as C and C++, Java, or, Visual Basic, why? Stop. Into instructions that the hardware can execute. Listen, I have to ask a question. Has anyone here ever used Visual Basic? I've used Visual Basic before. Has anyone here ever used it? Okay. Zymos, you've used it. Please tell me, is it not the worst thing in the world, the fact that if you write something that's syntactically incorrect, it immediately creates a pop-up telling you what's wrong? Why does it do that? You can't remember when you used it. Okay, listen, I did an internship and I was automating a bunch of stuff there, and they had a bunch of Excel spreadsheet stuff, and so I wrote some VBA. I couldn't take it. I did not have fun. It was not fun. But it's okay. This is an Engineering Today promise. This is even a Why So Green promise. We will never look at VBA on this stream unless somehow I get tricked to by it popping up in the book. And even then, I will delete that page from this printout version of the book. That's an Engineering Today promise. Okay, so let's move on. So, from high-level language to the language of hardware. Okay, to speak directly to electronic hardware, you need to send electrical signals. So, electrical signals, we mean on and off, ones and zeros. We mean, of course, binary numbers. And if you caught any of the stream yesterday, we talked about number systems for a bit. So we refer to each letter as a binary digit or bit. Usually we just call it a bit. Computers are slaves to our commands, which are called instructions. Okay, that's an interesting way to phrase that. You could have just said that computers only execute the instructions we give it. That works just as well. I don't know why you need to get so radical by calling computers slaves. Instructions, which are just collections of bits. So something like this could be an instruction. And we'll see how we actually encode assembly, or we can encode an assembly into instructions, and that assembly actually has set patterns that are predefined to translate from, English words into binary digits. Okay. So this is pretty simple. So then we can talk about an assembler. So the first programmers communicated to computers in binary numbers, but this was so tedious that they quickly invented new notations that were closer to the way humans think. So of course, initially we had, only binary, and then after we had binary, we had assembly, and then after assembly, we had higher level languages like C and Fortran, and then even later we have things like Python, right? Or Scratch. I've never used Scratch, and I will never use Scratch probably, but that's a funny thing to think about. Okay, so the lowest level that we generally care about today is assembly. We don't need to ever code anything just in binary. Sometimes we need to edit binary files, but usually we can get away with just editing some assembly. Okay, so let's see. So using the computer to help program the computer, the pioneers invented software to translate from symbolic notation to binary. So that's what an assembler does. So when you write down assembly code, you give that to an assembler. That assembler is actually what turns it into binary. So it translates, the language that you write into binary, just like how a compiler will translate your high-level code, such as C, C++, into assembly, but then the assembler has to take it to binary. Okay. The instruction tells the computer to add two numbers, A and B. The name coined for this symbolic language is assembly language. Okay, and then when we're talking about these binary strings up here, we're going to call that machine language. So that's pretty easy to understand. So we assemble assembly language into machine language. So although tremendous improvement, assembly language is still far from the notations. So that's where we get into high-level programming languages like we talked about. And this is abstraction. This is that key concept that we were talking about earlier. Hey, look, there's a pretty picture of abstraction. So a portable language like C, C++, Java, not Visual Basic. We're not going to talk about Visual Basic. That is composed of words and algebraic notation that can be translated by a compiler into assembly language. Okay, pretty cool. Pretty cool. So here we go. We've got C. We've got an equation for swapping. And then this is given to a compiler. This is turned into an assembly language. So it's going to have some function called swap still. And the way that this will work in assembly is that when swap needs to be called, there'll be a branch someplace where it'll tell the program counter to jump to this function or branch to this function. And then it will get here. And then it will do the same operations here. And so here we're doing some loads, and we're doing some stores, and we're doing an add. And then we have this JALR, and we'll go into what these mean later. So this is going to be jump and link return. Okay. And so we'll go into what jumping and linking when you return means later. And then the assembler is going to take this and put it into a bunch of binary bits that the computer will be able to understand. Okay, so this is a real world example and it's pretty neat to see. So let's see. So basically what we're going is from a plus b to something that's in assembly, such as add a comma b, and then we turn that into ones and zeros. That's how you can think of this. So let's talk a little bit about high-level languages. So high-level programming languages offer several important benefits. First, they allow the programmer to think in a more natural language, using English words and algebraic notation, resulting in programs that look much more like text than tables of cryptic symbols. Okay, that makes sense. Moreover, they allow languages to be designed according to their intended use. Hence, Fortran was designed for scientific computation, COBOL for business data processing, Lisp for simple symbol manipulation, which Lisp isn't, I don't know how common it is to use Lisp anymore. I feel like not many people use Lisp anymore, and I feel like that's a little sad. I always wanted to learn Lisp, but I never have because I'm not a computer scientist. Okay, the second advantage of programming languages is improved programmer productivity. One of the few areas of widespread agreement in software development is that it takes less time to develop programs when they are written in languages that require fewer lines to express the idea. Okay, so what are we talking about here? So if we want to write a program that does something, we don't want to have to write 500 lines of code that, are mainly managing control flow. And what I mean by control flow is I don't want to have to write many lines of code that are simply saying very low-level tasks such as go here, go here, go here, going to different spots of the program. I want to be able to describe the algorithm, how it would work at a very high level, and I want everything underneath that high-level language when it gets compiled to figure that out for me. So conciseness is a clear advantage of a high-level language over an assembly language, and we can see that here. So here we wrote 4 lines of code, and we can see even with this simple example, we're going to 7 lines of code. So this is, almost 2x the number of lines of code to do the same function in assembly language as it took in a high-level language. That's the key idea here, and that's why abstraction is so important. Okay, what else do we have? The second advantage of programming languages is improved programmer. Okay, so we talked about this, productivity. The final advantage is the programming languages allow programs to be independent of the computer on which they were developed. This is another very important thing. It seems like it's less important in some circumstances, but for people developing software that's going to be sold commercially, it's very important. Basically, what they're saying here is that when you compile a language like this in C, how this output looks depends on what system you compile it on. So this code will only work if what you're running on uses RISC-V. If you're on an x86 architecture processor, this code will not work. Your processor will have no idea what these instructions mean because they're going to be encoded completely differently. So it's important that we have these high-level abstractions, because when we have these high-level abstractions, it can simply be compiled on someone's local machine, and now the assembly language is generated there instead of, where we're distributing, and we don't have to host, instead of having to host, in copies of the program in assembly, we just need to maybe host a single version written in C. Okay, so I think that's about all we have for this section. Okay, so 1.4, under the covers. Ooh, now we're getting actually really cozy in here. Now we're getting cozy. Okay. So now that we have looked below your program to uncover the underlying software, let's open the covers of your computer to learn about the underlying hardware. Okay, that's important. We want to know more about the hardware if we want to be good architects or even good software developers, if we want to run fast-moving software or software that executes quickly, and we do high-performance computing, we want to know the underlying architecture. In fact, it's necessary. So, let's see. When we come to an important point in this book, a point so significant that we hope you'll remember it forever, we emphasize it as identifying it as a big picture item. We have about a dozen big pictures in this book, the first being the 5 components of a computer that perform tasks of inputting, outputting, processing, and storing data. Okay, so this is a very easy thing to kind of understand. It's that, every optimization that happens in a computer, every single architectural detail is not weighted the same. And that's the same in life as well as in computers. So we really want to understand what are the important topics, what do we really care about. Okay, let me respond to a message real quick and I will be right back. Okay, and I'm back. So let's see. 2 key components of computers are input devices and output devices. So this is I/O, what we talked about earlier. So that's these first 2, inputting and outputting, such as a speaker and a microphone, like I'm talking into, is a input device. Pretty simple concept. Okay, so chapters 5 and 6 will actually talk about I/O. Here we go. This is our big picture. So down here we have a computer, and we'll see that we have, very important components in here. So we want to understand how things get into memory and into our machine that we're working on. Just as importantly, we want to know how things flow out of our machine. That way we know how does the outside world talk with this and how can we make this usable. Then we want to understand memory. We want to understand memory because when we're inputting something and outputting something, we want to understand where that's coming from. Then we want to understand the processor. And what I mean by understanding the processor, we want to understand what we put in memory, we're going to do something with it. We don't want to just put something in memory and then do nothing with it. Then it serves no purpose. So we want to understand the processor. So that means we want to understand the control. How does the processor know what to do? And then the data path. How does our inputs move throughout the system to and from memory so that it can both do some number crunching here in the processor, and then get back to memory so that it can be pushed out to the output. So this is really our big picture. And so the key outside things we want to look at is, okay, here's our code coming in. How does that code come into the computer? Or into specifically, how does it interact with memory and the processor? How is this code written? And then when we're actually running our designs, we want to see how do we evaluate the performance of our designs. That's also a very interesting thing that we want to look at. So through the looking glass. So the most fascinating I/O device is probably graphics displays. So they're talking about LCDs here. Anything interesting? Okay, we can skip a lot of this. We don't need to really care about what makes up an LCD. So there's rods when current is applied and no longer bend the light. Since the liquid crystal material is between 2 screens polarized at 90 degrees, light cannot pass unless it's bent. Today, most LCDs use active matrix that has tiny transistor switch at each pixel to control current precisely. Okay. So now that we know that each pixel is controlled by a single transistor, it's fairly interesting, but we're architects. Unless you want to design LCD displays, this isn't particularly interesting. Okay, active matrix display, sure. The image is composed of a matrix of picture elements, or pixels, of course, which can be represented as a matrix of bits, so called a bitmap. So this is what the computer sees. The computer doesn't know what a picture looks like, it just knows what a bitmap looks like. It knows what that math actually looks like, which is fairly interesting. Okay, so depending on the size of the screen and the resolution of the display matrix in a typical tablet ranges in size from 1024 768 by 2048 by 1536. Okay, so we're just talking about resolution here. Not that interesting. We can skip over this. Okay, well, this is more interesting. Now we're getting into how the architecture actually interacts with something like a display. So how does the hardware know how to calculate these things? So the computer hardware support for graphics consists mainly of raster refresh buffer, or something called a frame buffer. And so this is what stores that bitmap that's eventually going to be printed to the screen. The image to be represented on screen is stored in the frame buffer. So the frame buffer over here, it has the information for what all the pixels are going to look like and gets printed on the screen. And if we end up getting that permission to use that computer architecture book, we can really look at details of things like frame buffers. I think that'll be very interesting. Uh-oh. I got a message. Let's see. Let's see if I can respond to this really quickly. Okay. We'll try to wrap up this chapter so I can take this call back. Okay. Let's see. We'll finish this chapter and then I may take a quick break, get some water, and then I think I'll be back and we can maybe move on a little bit. I'll probably be here for another 2-ish hours, so that'll probably be good. Okay, so we can talk a little bit about touchscreens, and so how they differ from a simple screen where we're just writing to a frame buffer, because now we're taking input on something that's typically an output. So while PCs also use LCDs, the tablets and smartphones of the post-PC era have replaced the keyboard and mouse with touch-sensitive displays, which have wonderful user interface advantages of users directly pointing whatever they want to use, blah, blah, blah. Okay, so it just says that people are electrical conductors, and then an insulator like glass is covered with a transparent conductor. Touching distorts the electrostatic field, changing capacitance, and then it allows for multiple touches simultaneously. Okay. I was hoping they would have done more with this, but that's okay. You don't always win. You don't always get, exactly what you want. That's fine. We can continue on. We can push ahead. So let's see. Opening the box. So figure 1.7 shows the contents of an iPad 2 with the 5 classical components. Okay. I/O dominates this reading device, of course, because we have a giant screen, and it has speakers, and both of those are input-output, and it's got a button on it. It has multiple buttons for power and for the home button and for volume. It has input for, of course, the headphone. It's got an accelerometer, that way it knows how to spin when you twist it on its side. Wi-Fi and Bluetooth are considered I/O, of course. And then data path and controller, of course, tiny things. So when we're talking about, anything like data path and I/O, we're talking about stuff on, these tiny chips right here. In fact, probably not this. This is probably like the Bluetooth module right here, or the Wi-Fi chip, I would guess. I've never looked at the guts of an iPad, so I don't know. We can skip over that caption. Courtesy of iFixit. So if you want to learn more, go to ifixit.com. Never mind. I'm not going to say go to ifixit.com. I've never been there. Don't go there. I'm not endorsing them. Okay. Okay, so the small rectangles are, of course, integrated circuits. So we know that those little black boxes that we see on motherboards are integrated circuits, and we call those chips. So the A5 package seen in the middle. So A5 is just a standard package size. That's fine. So DIMM is another, just a package name. It's not specific. And same thing with DIP, which stands for dual inline package. I think SIP is also one single inline package, maybe. I don't know if that's actually a used term. Maybe it is, maybe it's not. That's fine. The processor is the active part of the computer, of course. I think everyone can kind of reason about that. And of course, for an actual computer, it adds numbers, test numbers, and signals I/O devices to activate. So there has to be some set process for when you turn on a computer, for when you turn on an iPad, for it to know what to do. So those basic fundamental types of applications are usually hard coded and built in to the computer itself with system management chips. Occasionally people call the processor the CPU, Central Processing Unit. So there's another acronym. So if you didn't know what CPU meant, it means Central Processor Unit. Sometimes people call it Central Processing Unit. Okay. So there's that A5 chip. So A5 is the processor. And then I don't know enough about what these other things are. So you've got a Toshiba part over here. This is Toshiba. This is probably a drive. So this is probably like a solid state drive. And then you have, okay, the similar size chip on the left. So I'm guessing that's this is going to be your memory. So 32 gig flash memory chip for non-volatile storage. Or I don't, yeah, I think they mean this one. Okay, that's fine. I think we're good. Okay, then we have a Broadcom chip over here. This is going to be something networking related. This is going to be your Wi-Fi. Or probably your Wi-Fi. Maybe your Bluetooth. Maybe both. I don't know. I don't think it's an accelerometer. This might be an accelerometer. Maybe. It's hard to tell without actually looking at the part numbers. Sometimes they tell you what it is. Okay. So let's look even deeper into the hardware now. So, descending even lower into the hardware reveals details of the microprocessor. The processor logically comprises two main components, data path and control. The respective brawn and brain of the processor, the data path, performs the arithmetic operations, and control tells the data path, memory, and I/O devices what to do according to the wishes of the instruction. So basically you have a data path, which performs the arithmetic, and the control, as it would sound like, controls the data path. Okay, do we have any questions so far on any of this stuff? This is still fairly introductory type architecture stuff. It should be fairly easy to comprehend, but I don't want anyone here getting lost early. I want you guys to really fundamentally understand these concepts. I'm having a great time. I'm really enjoying teaching. Teaching something that I'm enjoying more than I thought I would. Okay, so we can move on. So let's see what's going to be next in our lists of things to do. So the next thing we're going to look at is Okay, so this is going to be a breakdown of the A5 package. So this is going to be what your actual processor is going to look like. So processor data path 1, so these are going to be our cores. So this is a 4-core processor. We're going to have GPIO, of course, which is our general purpose input output on the outside. So these are just going to be pins that we're going to be connecting to other places. We've got some more I/O here, so just input output. We have, oh no, maybe I'm wrong. Sorry, I'm wrong. So it's a 2-core processor. These are just data paths. Yeah. So our ARM cores are our actual processors. So this is a dual core. Okay. And then we have our dual data rate SDRAM, and we'll probably go into how SDRAM actually works. Okay, so a guy from chat asked, Joe, wait, that's pre-recorded, right? You're not multitasking chat and this lecture. I'm absolutely multitasking. I'm doing a great job. Okay, thanks for the stream. It's too late. I'm going to watch the VOD tomorrow. Hey, that's a-okay. Listen, the VOD's going to be up for you. You know, all I hope is that you learn something, and I hope you have a pleasant sleep, and I hope you have a wonderful day tomorrow. Okay, for everyone else still staying in the stream, thank you for being here still. Let's continue on with what we're learning. So down here we have PLLs, and if you don't know what PLLs are, that stands for phase lock loops. So if I'm not mistaken, PLLs, or phase lock loops, is the components that are going to control the different frequencies that we need around the board. So not every chip runs at the same frequency. So RAM, of course, doesn't run at the same frequency as the cores are going to run, which don't run as the same frequencies as the ALUs are going to run, which don't run at the same frequencies as USBs run. So we need a way of generating different clock speeds. And so that's generally done, I think, by PLLs. I think that's what that's for. We have a video DAC. So this is going to be our digital analog converter. We have our audio input and output, probably. We have a Wi-Fi little block here, more input output, more general purpose input output, and of course these are going to be our processor data paths. So if I'm not mistaken, this is going to be things like ALUs and, you know, computational units. And we have digital logic blocks in here. And so it doesn't say what the rest of these things are, which mean only one thing. It means that Apple didn't want you to know what these are. Okay, so, and here we have more memory. So more double data rate SDRAM interface. Okay. So let's see. What else we got? So this is, like I said, this is this A5 package, this ARM processor used by Apple, which, like we had said previously, this is for iPad 2, I think is what they said. So another thing another thing that'd be interesting to understand is, from a security angle, what can be done to actually steal these chips and reproduce fake copies of these chips. So it's very interesting. There are actually machines now that can etch off layer by layer of an integrated circuit and look at it at a transistor level. And you can actually recreate a chip using these machines. So you can create a phony little processor or a phony arbitrary chip using some of these machines. So I find that to be very interesting. That seems like a very cool thing that can be done right now. Very scary from a security point of view, but a very interesting thing. Okay. So let's see what else we have. So let's move on. So DRAM stands for Dynamic Random Access Memory. So multiple DRAMs are used together to contain the instructions and data for the program. So we have instruction memory and data memory. That's important to understand. Okay, so memory built as an integrated circuit, that's DRAM. So we'll talk a little bit about how DRAM is actually constructed later. But this is going to be our densest memory object, because DRAM, if I'm not mistaken, takes only a single transistor and a single capacitor to store a single bit. So something like SRAM, which is what your faster memory is going to be made out of, uses something called cross-coupled inverters. And every inverter is, I think every inverter is 2 gates. And then there's also some capacitors in there. So you're already minimum 4x the size of DRAM. Okay. So access time is 15 nanoseconds. It's not bad. It's not great. It's not bad. And cost per gigabyte in 2012 was $5 to $10. So it's fairly cheap. That's what you need to understand. It's fairly cheap. Then we have our caches. So caches are small, fast memory that act as a buffer for DRAM. So we're not, pounding on DRAM all the time. We have caches as a buffer, and these are what use SRAM, which is static random access memory. So these are much faster but much less dense. Like I said, they're much larger than individual bit storage that DRAM has. The bit storage in SRAM is a lot less dense, but it's faster. So SRAM and DRAM are 2 layers of the memory hierarchy. Okay, so we're going to have SRAM up here at the top. So we can go ahead and write that down. It'll be important for us to remember. So up the top here, we have our SRAM, which remember is static random access memory. And then here at the second level, we have DRAM, which is our dynamic random access memory. And I wonder what's going to be down here. Get in and take a guess. I'll give you a hint. It's not hard. It's the only part that we don't have yet. It's going to be disk. Disk is the only thing we're missing from this. So we have SRAM and DRAM, and then at the bottom of the memory hierarchy, we have disk. Where are the regs? You generally don't consider regs in the memory hierarchy. No, regs aren't generally considered counted as memory. No. So generally, when you're talking about the memory hierarchy, you're talking about things that are shared. Registers aren't shared. I think you can do register sharing in certain things, but that's way more complicated. Generally, when we're talking about the memory hierarchy, we're talking about usually shared resources and things that store a lot more data. Okay. So as mentioned above, one of the great ideas to improve design is abstraction. So, like we said, abstractions. This picture. So, what are we talking about as far as abstraction? So, because of its importance, it is given a special name, the instruction set. So the instruction set architecture, or simply architecture of the computer. So that's what we mean when we're talking, that's one of the biggest abstractions that we're going to really talk about in this, when we go through this book, is the ISA, the instruction set architecture. The instruction set architecture includes anything programmers need to know to make binary machine language programs work. So this includes how do the high-level languages map to the instructions? What do the instructions do? How do the instructions encode into machine language, or ones and zeros? And then how that eventually gets executed by the hardware. So typically the operating system will encapsulate the details of doing I/O, allocating memory, and other low-level system functions. So that's what we mean by like system software. So that application programmers don't need to worry about such details. The combination of basic instruction set and the operating system interface provided for application programmers is called the ABI, or Application Binary Interface. So the ABI is how we're going to, how these applications are going to interface more directly with the hardware. So it's going to be through this ABI interface. Okay. So let's move on. Okay, so we've gone over the instruction set architecture, or ISA, and we've gone over application binary interface, or ABI. An instruction set architecture allows computer designers to talk about functions independently from the hardware. So this is important. If we're trying to talk to somebody about what a computer does, we don't need to teach them what hardware is before we teach them software. We want to be able to talk about things generally. like we've said so many times before. Okay. For example, we can talk about functions of a digital clock separately from the clock hardware. So we don't need to teach someone about what an LED is to tell someone that we set an alarm. Okay. So computer designers distinguish architecture from implementation. So let's try to keep that in mind. And what you can kind of see is this is something that's very important for all walks of life. If you're talking with anybody, just talk. We don't want to get lost in the weeds in a conversation. So if someone asks how we're doing, generally they're looking for a response such as I'm doing well, I'm not doing well, I'm very busy, I have tons of free time, I'm happy, I'm sad. We generally don't need to tell them, okay, here are all the things that led up to me being this way. So we can consider that the different levels of abstraction. So we have our emotions, and behind our emotions we have all the events that led us to having those emotions. Just like we have our high-level programming languages, and then we have our ISA, and then we have the hardware that the ISA runs on. Okay. So the big picture. So here we have another big picture moment. Both hardware and software consist of hierarchical layers using abstraction, with each layer hiding details from level above. One key interface between the levels of abstraction is the instruction set architecture. So this is a bridge between layers. The interface between the hardware and low-level software. This abstract interface enables many implementations of varying cost and performance to run identical software. Very interesting. Okay. A safe place for data. Okay. So I think we're getting fairly close to the end of the first chapter. So let's see if we can finish this out and then take a quick break. Thus far, we have seen how to input data, compute using the data, and display data. If we were to lose power, we could lose things inside memory if it's volatile. So that means that when it loses power, it forgets. So this is temporary storage. Otherwise, we have forms of storage, such as DVDs or magnetic tape, that are non-volatile memory. So that means if we lose power, they retain all of their information. And so this is an interesting thing because servers a lot of times have a lot of failover, so that if you lose power, they have batteries in some of the components so that even if you have things in memory, it will keep the things in memory just long enough to write them all to a tiny piece of flash memory, so non-volatile memory, so that when you regain power, it can write that back to where it was supposed to go, to the correct place. Okay. So to distinguish between volatile memory, used to hold data in programs while they're running, and non-volatile memory to store data and the programs between runs, the term main memory, so it's always going to be called main memory. I don't know anyone that calls it primary memory. And then also secondary memory. Secondary memory are things like DRAM and primary memory. So it says magnetic disks, so that's like 1975, like it says. So flash memory is more common things now to have flash. Okay. While slower than DRAM, it is much cheaper than DRAM. So yeah, flash is slower than DRAM, much cheaper than DRAM. So flash memory is the standard secondary memory of PMDs, personal mobile devices. Alas, unlike disks and DRAM, flash memory bits wear out after 100K to 1 million writes. So that's bad. So that introduces another thing to keep in mind with fault tolerance is we don't want to pathologically write to only a few bits because we're going to wear those out really quickly, and then we're going to have a limited space for where we can write our data after a while. So that's fairly interesting. So yeah, Here we're talking more about the memory hierarchy. Okay? So magnetic disk, also called a hard disk. And flash memory, slower than DRAM, but fairly cheap. So communicating with other computers. Let's see how much more we have in this chapter. I think we're fairly close. Okay. So I think we'll go through this one last section, and then I'm going to take a break for a little bit, okay? So communicating with other computers. We've explained how we can input, compute, display, and save data, but there's still one thing missing from today's computers. It's computer network. So this is a very important thing, and I'm actually going to do an entire course on this and probably do some streams on this. So networks have become so popular that they are the backbone of current computer systems. A new personal mobile device or server without a network interface would be ridiculed. You know, you can't have these things that are just in isolation. It doesn't make sense unless it's for some specific application that doesn't need to talk to anyone. So here are the advantages of networked computers. So communication, so we can exchange information at high speed. We can share resources instead of having to have everything on a single device. And we can access things over long distances, which is a very important thing. And then we have, we can talk about a couple other different key concepts, which is, so let's see, networks vary in length and performance. It can be up to, so Ethernet, perhaps the most popular type of network is Ethernet. So an Ethernet network can be up to 1 kilometer long and transfer up to 40 gigabits per second. Its length and speed make Ethernet useful to connect computers in the same floor of a building, hence an example of what is generically called a local area network. Okay. So local area networks are interconnected with switches that can provide routing services and security. Now, WAN versus LAN, wide area networks, cross continents and are the backbone of the internet. So, the big tunnel between, or the big pipe between Europe and the US, we got a giant fiber optic connection between the two continents. It'd be interesting to look at how those come to fruition. Okay, so networks have changed the face of computing in the last 30 years, both by becoming much more ubiquitous and by making dramatic increases in performance. In the 1970s, very few individuals had access to electronic mail, so email, internet, and web did not exist. So physically mailing magnetic tapes was the primary way to transfer large amounts of data. Doesn't that sound horrible? Man, that sounds awful. I can't believe they actually laid all the cable. Yeah, no, that's awesome, right? There's so many really cool things that once you start getting into computer architecture that you find out. And when you get to things like computer networks, just the amount of infrastructure that's been built is amazing. Okay, so as networking technology improved, it became considerably cheaper to move and had significantly higher capacity. So standard local area network developed 30 years ago was a version of Ethernet that had a maximum capacity of 10 million bits per second, typically shared by tens, if not hundreds of computers. So now, local area network offer 1 to 40 gigabits per second shared by a few computers, and then optical communications technology. So it'd be interesting to do a little stream on fiber optics. I know a little bit, not a ton, but it'd be interesting to look at. So we've got a dramatic rise in deployment of networking combined with increasing capacity, making it central to the information revolution. For the last decade, another innovation in networking is reshaping the ways computers communicate. So wireless technology, that's what we're talking about. The ability to make radio in the same low-cost semiconductor technology. So CMOS, which stands for complementary metal oxide semiconductor. So CMOS is combinations of NMOS and PMOS together. So used for memory and microprocessors, enabled significant improvement in price, leading to an explosion in deployment. So how did this lead to a significant improvement in price? Can anyone answer this in a very simple way? You can answer it in two words. Who gets the bonus points by being able to answer it? Anyone going to get the bonus points? Come on. You guys can do it. Low power? Low power is not going to change how much it costs. Anyone else? I'll let one more person answer. If not, I'll go ahead. Or if you want to give another answer, that's fine. 2 words, and I'll give you a hint. It's one of the 8 key concepts of why it's cheaper. Okay, that's fine. So, we're talking about why wireless technology, once it started using CMOS or transistors, became way cheaper. And so I'll tell you why right now. Moore's Law. So if we start making network technology with transistors, yeah, that's correct. So smaller, Moore's Law. So the basic idea is we get twice as many transistors for the same money, or for the same amount of money. So if we use something like that, that means that our price is going to decrease every generation or 2 years by about half for the exact same product. So that's why, you started using CMOS. It was a significant improvement in price. So Moore's Law is the answer. So smaller is also correct. Low power is not a bad guess, but low power typically doesn't influence price. So currently available wireless technology. So IEEE standard is 802.11, which is 1 to nearly 100 million bits per second. Okay. So that's pretty good. So we learned a lot in this session. We learned a lot about some introductory into computer architecture and some foundations. So let's check yourself. So semiconductor DRAM technology, flash memory, and disk storage differ significantly. For each technology, lists its volatility, approximate relative access time, and approximate relative cost. So, like we said, DRAM is volatile, and then flash and disk are both non-volatile, meaning we're not going to lose it if we lose power. And access time, we know that disk is always going to be the slowest. We know that DRAM out of these 3 is going to be the fastest. And we know that flash, while not the slowest, is still going to be slower than DRAM. Okay. So after a quick break, we're going to get back and we're going to talk about technologies for building processors and memory. So we're going to talk about performance analysis, and we're going to talk a little bit about very large system integration, VLSI, which is really just chip design. So we've gone through 84 pages of this book so far. So I think we're making good progress. Okay. So I'm going to cut the stream for a little bit. I want to thank you all for joining us if I don't see you when I return. But I hope you all have a wonderful evening, and thank you for joining the stream. So in probably about a half hour, we'll start the stream back up. And if you're able to join me, I'll make sure to try to post around that I'm starting the stream again. But I hope you have a wonderful time until I return. Like I said, I'll be returning in about a half hour or so. But if you're not here, I hope you learned something today. And listen, I got a couple seconds. If you have any final questions before I grab some water and make a phone call, I'd be happy to answer. Or if you want a little fun fact, let me know what you want a fun fact on, and I'll see if I can help you out. Since I'm doing real-time streaming, I'll give you about 30 seconds. See if there's anything. Hillside, thanks for the stream. No problem, man. Live stream sniper. Hey, if I don't see you again, thanks for joining the stream. Fun fact, please. Okay, let's see if we can come up with a fun fact. Here's a very interesting fun fact. So we know that going to disk storage is incredibly slow, and we're talking tens of thousands, maybe even hundreds of thousands of clock cycles. So there's actually a very fun fact that the communication rate for I/O, we can build systems that have incredibly fast communication between systems, like physically between different systems. So there's actually been designs where we have a pooled cache. So we have a system that has extremely fast memory as a shared resource. So a processor can actually send a request over I/O to this shared resource pool, access something in the shared resource pool, have it sent back over that link back to the processor, and orders of magnitude faster than going to disk. So basically, it's faster to go to another computer than it is to actually go to your own disk. So there's a quick fun fact, and we'll go into why that is in a bit. Yeah, really cool. Really cool, right? We'll go into that sometime. That's actually a really cool idea, and I think I saw a paper on that. It's not my area, but I wouldn't mind going over a paper on that. I think it'd be really cool. Not in the same processor, going over a network. So not like over like the internet. I'm talking about talking about systems connected together. So this is about RDMA. So RDMA is remote direct memory access. So it's direct memory access from the memory of one computer into that of another. So if you want to look that up, it's RDMA. All right. I will see you guys in a bit. And as always, learn something new. Ciao.